And here we go, Chapter 13, Section 2, Ozone Shield. Your essential question kicking us off is, why does the threat to our ozone continue to this day? Figured out what it was, we've done things to deal with it, but why does it persist? Now, the ozone shield, ozone layer in a sense. This is a layer of ozone molecules in the stratosphere, somewhere around 15 to 40 kilometers, depending on weather conditions, lots of various things. It's a molecule made up of 3 oxygens. What you and I breathe in is O2, ozone is O3. Well, it's a thick layer of ozone, and it winds up blocking, absorbing UV radiation, which is harmful to organisms. It's what causes you and me to get sunburned, for instance. It damages our skin. It can also damage the genetic material. It's where people can also get melanoma or skin cancer from. This UV radiation penetrating our skin, there's a lot of benefits to it at small doses, but too much causes problems. So, with the ozone layer shielding the Earth's surface from most of the UV radiation, the ozone in the stratosphere kind of acts like a sunscreen, if you will, for the entire planet, blocking most of the harmful UV rays. The chemicals that cause the ozone depletion were chlorofluorocarbons, also just going to be referred to as CFCs. And I will go back and forth and say chlorofluorocarbons, CFC, same thing. These are hydrocarbons, okay? So hydrogen with a carbon bonded to it. You and I are hydrocarbons, logs, lots of things are. It's a fairly common compound, if you will, where some or all of the hydrogen atoms have been replaced with chlorine and fluorine. So like methane, CH4, well, you can't have C, then fluorine 3, chlorine 1. We're replacing the hydrogens with fluorines and chlorines, and it creates a stable compound, and we used it in a lot of things. They were used in coolants. Freon, like when I was growing up, you put Freon to recharge your air conditioners, what was in refrigerators, etc., made things cold. We also used it in a lot of propellants, virtually anything that you spray, you held down the can, like paint or hairspray or WD-40, the list just goes on and on. It was used as an accelerant in a lot of containers, so refrigerants, coolants, in air conditioners, refrigerators, freezers, and then in aerosols. They are now restricted. They are virtually banned in most places, except for very small uses where we don't have anything else that really can suffice. But we have banned these products since they destroy the ozone layer. Now, at the Earth's surface, when we made these in the lab, if you will, they were incredibly chemically stable. They remained whatever they were, CF3C1, carbon, 3 fluorides, 1 chlorine, or a carbon and 4 chlorines, different ways that they were bonded, made together. Incredibly stable. They didn't combine with other chemicals, they didn't break down into other substances, and they were fairly easy and cheap to make. However, when these molecules made their way up into the stratosphere with high levels of UV radiation, they began to break apart. It's just something we didn't think to test for down here on the planet Earth. And we were using for a long time before we realized anything was going on. You can't see the ozone layer, not with your naked eye, etc. We just didn't know what was going on. Now, once the CFC molecules break apart into some of their constituent parts, carbon, fluoride, and chlorine, then they began to destroy this protective ozone layer. Now, this is what actually happens. Once again, a CFC can contain anywhere from 1 to 4 chlorine atoms. I'm going to throw a picture of one up back here. This one has 1 carbon, that's the big gray one in the center. It has 3 blue molecules, in this case those are going to be fluorine, and it has 1 green atom attached, and that's going to be our chlorine. What happens is, in the presence of UV, a chlorine atom breaks off. Well, that chlorine atom winds up being fairly reactive, especially with ozone. Ozone is fairly chemically unstable. It doesn't really like to be ozone. It would prefer to be oxygen, O2, or something else. So when the chlorine atom comes in contact with an ozone, the ozone breaks apart into O2, oxygen, and chlorine monoxide. One chlorine, one oxygen. Then that chlorine monoxide, when it comes in contact with another ozone molecule, it breaks apart again, and the ozone turns the ozone, O3, and the CO breaks apart again into 2O2, O2, O2, and the chlorine is set free again to repeat the cycle. And it just goes on and on and on and on until chlorine either bonds with something else and it is more stable and it ceases it, or it drifts out of the stratosphere, no longer causing problems. It has been estimated that a single chlorine atom can destroy as many as 100,000 ozone molecules, because it's just an endless cycle of the chlorine bonding to an oxygen and then bonding to another ozone, freeing up the chlorine, going over and over and over. In 1985, studies by scientists that were working in Antarctica were able to reveal that the ozone layer had thinned by somewhere between 50 to 98%. So this ozone hole is a thinning of the stratospheric ozone, and it occurs over the poles, North Pole and South Pole. After the results were published, NASA reviewed data. So we found out, we went back and began looking at data from satellites, specifically weather satellites, and we could trace it back to 1979 when it began to thin. We had been using the chlorofluorocarbons. We realized it was thinning. We were able to go back and see when it started, and we had to begin to piece together what was happening on. Part of the problem was the concentration of ozone fluctuated during the year. In the winter times, it thickened up and there wasn't a hole. But in the spring and summer, it thinned way out and the hole appeared. So we were having issues trying to determine what was going on. In 1997, ozone layers over part of Canada were like 45% below normal. In northern Canada, near the poles, the ozone hole had been spreading out. Now, following the discovery, once again, back in '85, scientists, governments, and chemical companies began developing ways to prevent the ozone hole from growing. As a result, the ozone in the stratosphere is no longer decreasing. In fact, it's healing, it's getting thicker. If you take a look at the picture here, back from 1980, now the really dark part in the center of that really is Antarctica, the continent, but then you can see that blue ring growing out from it. This is the ozone hole, taken in times during the spring and summer. So from 1980 to 2000, expanding out. Now, according to an article from 2018, it is estimated that the ozone layer will totally heal within 50 years. Why so long? We've banned the chemicals. We're not using them anymore. It's just because those chlorine atoms up in the stratosphere last so long. So how does it form? Now, during the dark polar winter, once again, during the winter time, it's winter at North Pole, summer at South Pole, and vice versa. But during the winter months at the poles, the sun doesn't shine up there hardly at all because it's tilted away from the sun. So we get a long, dark winter, very cold. We get strong circulating winds over Antarctica. We refer to these as the polar vortex. And they isolate the cold air from the surrounding warmer air, circling up, and it kind of keeps warm air at bay. And the air within this vortex grows incredibly cold, and it forms polar stratospheric clouds. They form at altitudes above 21,000 meters up, incredibly high. We do not find most normal clouds in this range. Only occurs during the Arctic winter maybe very early spring, the air temperatures have to be below -80. It's incredibly cold, and these polar stratospheric clouds form, and the products of the CFCs get converted into molecular chlorine. Basically, the chlorine winds up getting frozen in these clouds. So the chlorine gets trapped in the clouds, and the ozone is free to heal itself, if you will. But then, when the sunlight returns to the pole in spring, well, the molecular chlorine is split into 2 chlorine atoms by the UV radiation again. Sunlight's coming in, more UV radiation, and then the chlorines go about their business of rapidly destroying the ozone. And this destruction of the ozone causes a thin spot, or what we call the ozone hole, and it lasts for several months. Fortunately, summertime is fairly short at the poles, so the hole doesn't have as long to grow. And if you're thinking, well, if it's the ozone is being produced up in the air, but down here on Earth we produce ozone, but we refer to it as air pollution. Can't this ozone help that ozone? Well, not really. Ozone is very chemically reactive. It's O3, but it doesn't really like to be O3. It prefers to be O2 or something else, like CO2, carbon dioxide, or H2O. Oxygen will bond with many other things, and O3 is not one of its more stable forms. So the ozone produced by pollution down here, by the time it begins moving up through our atmosphere, it never reaches the stratosphere because it'll get changed into something else. The ozone gets destroyed, either goes back to being oxygen or bonds with chlorine down here or something else, and it doesn't make it up. So the ozone that we create down here on the Earth, which creates smog, never makes it up to the ozone layer to help us there. So ozone really high up is good. Ozone way down low in the troposphere near us is bad. So just keep about, when you think about ozone, think about its location. Stratosphere, good. Troposphere, bad. Anyway, as the amount of ozone in the stratosphere decreases, more UV light is able to pass through the atmosphere. More UV light means I'm going to get sunburned much easily. Propensity of me getting skin cancer is higher, etc. Now, UV can be dangerous to humans, but it's also dangerous to anything else that's living because it can damage DNA. Once again, it's damaging the skin cells. It's literally cooking them, if you will. And that radiation can damage the DNA, which is why some people get skin cancer, etc. If it can hurt humans, well, it can hurt other things as well. This exposure to UV radiation makes the body more susceptible to skin cancer. Well, it's also that way for other living things. High levels of UV radiation can kill phytoplankton. Phytoplankton are the base of the food chain in the ocean. So anything near the surface, if we get high levels of UV radiation, it can kill them as well. Loss of phytoplankton disrupts, obviously, the food web. Also, the number of phytoplankton would cause an increase in the amount of carbon dioxide. We get a lot of phytoplankton dying off. Well, they're plants, right? They're taking carbon dioxide in, releasing oxygen. So killing off lots and lots of phytoplankton has huge issues for not just a food source, but for oxygen creation and pulling carbon dioxide out of the air. We believe that increased UV light could be a factor in the decline of amphibians. We have seen a serious uptick in the extinction and decrease of amphibian species around the world. It's been very concerning and alarming, the number of species of amphibians that are going extinct. And we feel that this UV light may be a serious factor in that, the cutting down of it. So this is one of these human-led events causing extinction events around the world. This increased UV radiation could also reduce the survival of amphibian eggs. So once again, amphibian eggs are very, they're just kind of like jelly-like. There's not much protecting them. Doesn't have a hard coating like lizards or other organisms. Amphibians just tend to be what we call an indicator species because they're so environmentally sensitive. So if something's happening to amphibians, we need to pay attention because something's going to start happening on a larger scale. UV light also damages plants. It interferes with photosynthesis. So the plants need light, and UV is part of that, but too much of a good thing can be a bad thing. So once again, it can kill organisms, and it can also damage their ability to do photosynthesis properly. Now in 1987, a group of nations came together in an agreement called the Montreal Protocol. And the effort of this was to sharply limit the production of CFCs. We came together and said, it's actually okay if we stop making CFCs where they're not going to be used. A lot of places were banned from using the product unless you had, like national defense level reason to have it. But then they were simply limited how many were produced. Everybody had to shift to something else. Many people consider the ozone protection of that international agreement one of our environmental success stories. We have successfully come together, realized what the problem was, came up together with a solution as a country, as countries, if you will, came up with a protocol, agreed to cease making the chemical that was causing the problem. We continue to work to protect the ozone layers because those CFCs remain active for so long. But this is one of these rare success stories that we identified the problem, we found out what the problem was, we all got together to work towards a solution, and we actually made the agreement. And the ozone hole is healing. Oh, there you go. Everything you may have wanted to know, but were afraid to ask about the ozone layer. That's it for today. We'll see you next time.